So Kepler's third law of planetary motion says that the time that it takes a planet squared to orbit the sun is proportional to how far away it is from the sun cubed. And to turn a proportion into an equation, you need what's called a constant of proportionality. So time squared is equal to some constant k times r cubed. And again, Kepler just solved everything like relative to the Earth, right? So he never knew the value of this constant here. So I think maybe we should figure it out today. And just think through it a little bit here. All right, so let's think about like the force of gravity is equal to G(m)(m) over r squared. Okay, so this describes the force of gravity between two objects like a sun and a planet. And the force that keeps things moving in circles is the centripetal force. It's provided by gravity, and it's equal to mv squared over r. Okay, so this is the equation for centripetal force. Okay, centripetal acceleration, center-seeking acceleration. And so gravity is providing the center-seeking force to keep planets sort of moving around circles. So we can set these equal to each other. We see that G(m)(m) over r squared is equal to mv squared over r. This m cancels, right? We can divide both sides by m, so we just get Gm over r squared equals v squared over r. Or rewrite that as Gm over r squared equal to v squared over r. I can multiply both sides by r. And then cancel out one of those and get rid of that. So I have, oh, did I do that right? Multiply both sides by r. So it's r over here, so you have r squared. So then that cancels one of those and just have r. So you have v squared equal to Gm over the single r. What is the velocity of something moving in a circle? Velocity, what's the distance something travels if it moves in a circle? 2 pi r over the time t, right? Velocity is distance divided by time. So velocity is the circumference of a circle divided by time for a planet. I'll plug that in for v over here. So we've got 2 pi r over t, quantity squared, equal to Gm over r. This becomes 4 pi squared r squared over t squared equal to Gm over r. And now we'll kind of clean this all up. Multiply those sides by t squared. And we want to get that by itself, right? We're heading towards this. We want, what is the value of this constant k here? We just kind of see we're getting there, right? It's looking better. So then those go away. I got t squared. Now when I multiply this side by this term, r over Gm. Because it's convenient. If I multiply this side by r over Gm, it gets rid of all this other stuff I don't want. And I'm allowed to do that as long as I do it to this side, right? The rule of algebra. So now r divided by r is 1, g divided by g is 1, m divided by m is 1. 1 times t squared is just t squared. Good. And then over here I've got the 4 pi squared. I've got r squared times another r, so I've got r cubed over Gm. Bingo. That's the constant that Kepler himself never knew, but we can calculate it here today because, as Newton said, we stand on the shoulders of giants. Okay? Newton said that. How have we been able to see so far? Because I've stood on the shoulders of giants. Galileo, Kepler. Okay, so Kepler knew it empirically by looking at data that Tycho Brahe had collected about the heavenly bodies. He said, hey, things orbit in ellipses. The area they sweep out in equal times are equal, and the orbital period squared is proportional to the distance from the sun cubed. You kind of recognize, like, hey, you could draw a line. If you plot the orbital period squared against r cubed, all the planets fall into a line. Okay, and the slope of that line is 4 pi squared divided by Newton's universal gravitational constant, and this would be the mass of the sun. Okay, where everything is ordered. But yeah, the spaceship as well. like plot the orbital period against the radius. I mean, you could look up data for the planets and see that that will fall into, you know, a line, and then you could do the slope and then see does it equal, like we could crunch this number right now, like what is the actual value of this? How much time do we have? I don't know if you want to do that right now. It's 2:03 p.m. Friday the 13th, but we can get a little bit crazy and do that. So 4 times pi times pi, let me tell you what g is if you don't remember, 6.67 by 10 to the negative 11. And then the mass of the sun, we all know, is 1.989 by 10 to the 30 kilograms. About 1 million times more massive than the Earth, or any planet in our solar system. All right, so here's the values you need for this one. We're just calculating this K constant, right? Because it sort of says, here's the number we multiply how far away from the sun the planet is cubed to give us how long a year is squared. That's the relationship. This is how we know, for example, Pluto orbits the sun in 150 or 250 years. You know, Mercury orbits the sun every 88 days, okay, compared to the Earth. So all ratio, okay, to calculate this, you all have that start, that's fair, because I haven't done it yet, and I don't think today's going to be the first one. Ready? I'm ready for math. It's the electricity. Yes. That is electricity. Anybody got it? Electricity. I didn't think so. Hey. Even when students do beat me to the calculation, because sometimes students are like, I'm gonna beat them today, right? Like, you know, Logan's beat me to the door at the beginning of the year. Do a good job with students to the door. Then that's all COVID. We can't have students touching high contact surfaces unless I'm playing a game of chess out there. Oh, that's all recorded right now. I'll edit it out later. Even when a student beats me in the calculation, I'll stall them. You know, it's kind of like, I think the answer, you know, just start, you know, oh, it's chalk on the top, you know, until I get it. And it's like, okay, to ensure my victory. I think years ago, I was in my master's program, I had to do I was taking a class on creativity in education. And my daughter helped me with an assignment where we had to make a creative video. And she was a rock, paper, scissors champion. I was like, oh, I hear you're the rock, paper, scissors champion. You've never been beat. She's like, yeah, that's right. But all right, I challenge you. Ready? Well, rock, paper, scissors, shoot. And it's like, I throw paper and she throws a rock. And it's like, aha, beat you now. The dispute comes to an end. And she's like, yeah, this isn't a rock. Scissors. How did you do that? You know, like, she beats me every time. All right, anybody got it? Everybody gave up? 2.975 by 10 to the negative 9. The units, I guess, Newton meters squared per kilogram squared, but then we're divided times another kilogram. So, and these are all in the denominator. So the units would be kilograms cubed per Newton per meter squared. There you go. Almost electricity.